Hello students, so today we are going to deal with new topic Fourier series. Before we have to look back into the topic integral transform. In brief, the basic aim of the integral transform method is to transfer a given problem into another problem which is easier to solve, and this method is applicable for ordinary as well as partial differential equation. In the case of ordinary differential equation, integral transform method convert the differential equation into an algebraic equation which is easier to solve. In the case of partial differential equation, the integral transform method transform the problem into another problem with one variable less. So when moving back to Fourier transform. Joseph Fourier is the founder of Fourier transform. As we all know that the Taylor series represents the functions are valid only for those functions which are continuous and differentiable, but there are many discontinuous periodic functions which requires to express in terms of infinite series containing sine and cosine terms. So that's why we use Fourier series. Fourier series, which is an infinite series representation of such functions in terms of sine and cosines. Fourier series is a very powerful method to solve ordinary and partial differential equations, and particularly with periodic functions appearing as non-homogeneous terms. Before that, we have to know what is periodic function. If the value of function f of x repeats itself at equal interval of x, then fx is said to be periodic function of x. That is fx equal to f of x plus t equal to f of x plus 2t equal to f of x plus 3t, etc., where t is the period of the function f of x. Example, sin x, cos x, sec x, cosec x to t equal to at period equal to 2 pi. Now we have to look the basic formula of the Fourier series. A non-sinusoidal periodic function can be expressed by the sum of set of simple oscillating function or periodic function, that is mainly the combination of sine and cosines, and this series is known as Fourier series, and that is f of x equal to a0 by 2 plus sigma n equal to 1 to infinity a n cos n x plus sigma n equal to 1 to infinity b n sin x. And Fourier suggested the series based on the principle of superimposition. In equation we can see that the sine and cosines are periodic functions, hence the f of x is also a periodic function, where a0, an, bn are the constants and that are known as Fourier coefficients. The condition for the f of x. Conditions for f of x. The function f of x has only a finite number of finite discontinuous and only a finite number of extreme values. Such functions are called piecewise regular functions, and these conditions are called Dirichlet's conditions. And if f of x has the following conditions, that is, first one is f of x is bounded and single value, and second one is f of x has at most a finite number of maximum and minimum in the interval, and third one is f of x has almost a finite number of discontinuous in the interval. Example, sin inverse x, we can see the function sin inverse x can't be expressed as Fourier series, and it is not a single valued function. Also, the tan x in the interval 0 to 2 pi cannot be expressed as Fourier series because it is infinity at x equal to pi by 2. And these are the useful integrals for solving problems. That is integral 0 to 2 pi sin nx dx equal to 0. That is integral 0 to 2 pi cos nx dx equal to 0. Integral 0 to 2 pi sin squared nx dx equal to pi. In the case of cos squared nx dx equal to pi. pi integral 0 to 2 pi sin nx sin mx dx equal to 0, where m not equal to n, and 0 to integral 0 to 2 pi cos nx cos mx dx equal to 0, where m not equal to n, and integral 0 to 2 pi sin nx cos mx dx equal to 0 to 2 pi sin nx cos nx dx equal to 0, that is m equal to is equal to 0, that is. Last one is sin n pi equal to 0 cos n pi equal to minus 1 raised to n. An evaluation of Fourier coefficients. We know that a0, an and bn is known as Fourier coefficient. Suppose the function f of x is defined in the interval 0 to 2 pi. Then the Fourier series f of x can be written as a0 by 2 plus sigma n equal to 1 to infinity an cos nx plus sigma n equal to 1 to infinity bn sin nx, where a0 can be written as 1 by pi integral 0 to 2 pi f of x dx, and an equal to 1 by pi integral 0 to 2 pi f of x cos nx dx, and bn equal to 1 by pi integral 0 to 2 pi f of x sin nx dx. If the function f in case 2, if the function f of x is defined in integral minus pi to pi, where the a0 can be written as 1 by pi into integral minus pi to pi f of x dx, and an equal to 1 by pi integral minus pi to pi f of x cos nx dx, and bn equal to 1 by pi integral minus pi to plus pi f of x sin x dx. And case 3, if the function is defined in the integral 0 to 2l, then the Fourier series f of x equal to a0 by 2 plus sigma n equal to 1 to infinity an cos n pi x by 1 plus sigma n equal to 1 to infinity bn sin n pi x by 1, where a0 equal to 1 by 1 integral 0 to 2l f of x dx, and an equal to 1 by l integral 0 to 2l f of x cos n pi x by l dx, and bn equal to 1 by l integral 0 to 2l f of x sin n pi x by l dx. And last one, case 4, if the function f of x defined in the interval minus l to plus l, and the a0 can be written as 1 by l integral minus l to l f of x dx. In case 3, we can see the interval is 0 to 2l, and a0 becomes 1 by l. Here the interval minus l to plus l, a0 becomes 1 by l integral minus l to l f of x dx, and an equal to 1 by 1 integral minus 1 to plus 1 f of x cos n pi x by 1 dx, and bn equal to 1 by 1 integral minus 1 to 1 f of x sin n pi x by 1 dx. So we can see that in each cases Fourier series and its coefficient varies depending on the interval. So you should remember these cases properly. And nature of Fourier series for even and odd function. A function f of x even when f of x equal to f of minus x, and in the case of function is odd function, f of x equal to minus f of minus x, and cos x is the example of even function, and sin x is an example for odd function. And what nature of Fourier series for even and odd function? We already said that function is said to be even if f of minus x equal to f of x. For even function, we can see that the integral minus pi to plus pi f of x dx can be written as 2 into integral 0 to pi f of x dx. That is, a0 can be written as 2 by pi integral minus pi to plus pi f of x dx can be written as 1 by pi integral 0 to pi f of x dx. And an equal to 1 by pi integral minus pi to plus pi f of x cos nx dx equal to 2 by pi integral 0 to pi f of x cos nx dx. and bn. 1 by pi integral minus pi to pi f of x nx dx equal to 0, and this series will contain only cosine terms, and the Fourier series can be written as f of x equal to a0 plus sigma n equal to 1 to infinity a n cos nx. There is no sine terms in even function. And in the case of odd function, we can see that there is only in this series will contain only sine terms, and the Fourier series expansion can be written as f of x equal to sigma n equal to 1 to infinity bn sin x. In the case of odd function, we get a0 equal to 0 and an equal to 0, and in the case of even function, we get that bn equal to 0. Find the Fourier series of f of x equal to x squared plus 2, and the interval is minus pi to pi. There is a missing of pi in this question. So find the Fourier series of f of x can given by x squared plus x. We already know the general formula Fourier series f of x equal to a0 by 2 plus sigma n equal to 1 to infinity a n cos nx plus sigma n equal to 1 to infinity b n sin nx. So we have to find the value a0, a n and b n Fourier coefficients. Therefore we know that a0 equal to 1 by pi integral minus pi to plus pi f of x dx. Here f of x equal to x squared plus x, that is 1 by pi integral minus pi to pi x squared plus x dx. By integrating, we get 1 by pi x cubed by 3 plus x squared by 2 integral minus pi to limit minus pi to plus pi. By applying limit class, we get that a0 equal to 2 pi cube by 3. Now we have to find an. An equal to 1 by pi integral minus pi to pi f of x cos nx dx. By substituting the value of f of x, we get my 1 by pi integral minus pi to pi x squared plus x cos nx dx. By integrating and putting limit last, we got that 4 into minus 1 raised to n by n squared. Similarly, we can find bn equal to 1 by pi integral minus pi to pi f of x sin nx dx. Here f of x equal to x squared plus x. By integrating and applying limit last, we get that minus 2 into minus 1 raised to n by n. So the Fourier series of f of x squared plus x equal to pi squared by 3 plus sigma n equal to 1 to infinity 4 into minus 1 raised to n by n squared cos nx minus 2 into minus 1 raised to n by n sin nx. Now the another topic is Fourier integral. The Fourier integral of the f of x is given by f of x equal to 1 by pi integral 0 to infinity integral minus infinity to infinity f of t cos lambda t minus x into dt d lambda. The Fourier integral of f of x. Now the Fourier cosine integral of f of x is given by f of x equal to 1 by pi integral 0 to infinity integral minus infinity to plus infinity f of t cos lambda t into cos lambda x dt d lambda. By taking outside cos lambda x, that is 1 by pi integral 0 to infinity cos lambda x integral minus infinity to plus infinity f of t cos lambda t into dt into d lambda. By that equal to 2 by lambda integral 0 to infinity cos lambda x integral 0 to infinity equal to f of t cos lambda t dt d lambda. Here the variable 2 is there only because the integral minus infinity to plus infinity is changed as integral 0 to infinity. That is Fourier cosine integral can be written as 2 by pi integral 0 to infinity cos lambda x integral 0 to infinity f of t cos lambda t dt d lambda. Now similarly, Fourier sine integral of f of x can be written as same as the Fourier cosine integral, and from this we get that f of x equal to 2 by pi integral 0 to infinity sine lambda x integral 0 to infinity f of t sine lambda t dt d lambda. Now let's look into one application of Fourier series, that is Fourier series of square wave. How the Fourier series acting on a square wave. In this slide we can see a square wave, and the function f of x can be written as minus k in the limit minus pi less than x less than 0, and another function is k, that is 0 less than x less than pi. We already know the general formula of Fourier series is f of x equal to a0 by 2 plus sigma n equal to 1 to infinity a n cosine x plus sigma n equal to 1 to infinity b n sin n x, and this is called as equation 1. And a0 equal to 1 by pi integral minus pi to plus pi f of x dx. Here f of x can be written as limits. Here the limits is minus pi to 0 and 0 to pi. That is a0 equal to 1 by pi into integral minus pi to 0 minus k dx plus integral 0 to pi k dx. By integrating we get 1 by pi into minus kx into minus pi to 0 plus k into x 0 to pi, and by taking outside minus k and applying limits we get that a0 equal to 0. And another we have to find another time an equal to 1 by pi integral minus pi to pi f of x cos nx, and here also an equal to 1 by pi integral minus pi to 0 minus k cos nx dx plus integral 0 to pi k cos nx dx, and by integrating and applying limit we can see that n sin n pi equal to 0, that is sin 0 equal to 0 and sin pi equal to 0. So here we applying upper limit and lower limit we get these sin n pi and sin 0 equal to 0, therefore an equal to 0. Now bn equal to 1 by pi integral minus pi to 0 minus k sin nx dx plus integral 0 to pi k sin nx dx, and here by integrating we get integrating and applying limit we can see that cos 0, we already know that cos 0 equal to 1 and cos n pi can be written as minus 1 raised to n. So here bn equal to 1 by pi into k by n into 1 minus cos n minus pi can be written as cos n pi. Cos n pi here we get that minus 1 raised to n, that 1 minus minus 1 raised to n minus minus of minus 1 raised to n minus 1, that equal to 1 by pi into k by n into 1 minus minus 1 raised to n minus minus 1 raised to n and minus into minus plus 1. So that can be written as k by n pi 2 minus 2 into minus 1 raised to n. By taking outside 2 we get bn equal to 2k by n pi into 1 minus minus 1 raised to n, that can be written as 2k by pi into 1 minus minus 1 raised to n by n. Substituting these values a0, an, bn in equation 1. So Fourier series we get that we already know that a0 equal to 0 and an equal to 0. Therefore Fourier series f of x can be written as 0 plus sigma n equal to 1 to infinity 2k by pi into 1 minus minus 1 raised to n by n sin nx. That is f of x equal to sigma n equal to 1 to infinity 2k by pi 1 minus minus 1 raised to n by n into sin nx. even if we substitute n equal to 2, 4, 6, that we even numbers, we get that we already know the minus 1 squared equal to 1. So the term 1 minus minus 1 raised to n by n equal to 0. So f of x equal to 0. If we substitute the value of n equal to 1, 3, 5 odd numbers, we get f of x equal to sigma n equal to 1 to infinity 2k by pi into 2 into sine 1x by 1 plus sine 3x by 3 plus sine 5x by 3. Therefore, we can see that f of x equal to 4k by pi into sine 1x by 1 plus sine 3x by 3 plus therefore equal to infinity. And this is the Fourier series of the square